Hello all, welcome back to AK Apt Logics. In the previous class we have discussed about the sorry, I have pasted in reverse. Okay, just a second. In the previous class we have discussed about the AND gate in behavioral model. Okay, in that I have discussed so many models using if else, using ternary operator, using case, and using normal boolean expression like that. And I haven't discussed about the TB how I have written it. Okay, if you want to know how to write the TB, then I recommend you guys to watch uh, the AND gate using gate level model. In that I have discussed how to write TB, and also I have discussed how to analyze the output that we have got through waveforms and through console. I have discussed it. So today in this class what we are going to discuss is we are going to discuss the most important thing, that is switch level modeling. Okay, for the AND gate, how we are going to model the switch level thing, switch level modeling, we are going to see it. So in every video I am going to tell you, right, the module name and the port list till semicolon, and then end module. Everything will be same for any levels of abstraction. Only the matter in between the semicolon and the end module is going to get changed according to the abstraction that you are going to choose. And there will be no change in TB. Same TB can be used for all the design codes of the same design with different levels of abstraction, only when your module name is not changed. Okay, if you change the module name in design code, then you need to change the module design module which is instantiated in the test bench. Okay, for example, if I am going to change the design module name as AND gate switch, then you need to change the instance name which you have instantiated, that is the design code which is instantiated in the test bench. Its name also you need to change, like AND gate underscore switch. If you are not going to perform any changes to the module name in the design code, then it is not required to change any changes in the test bench. Same test bench can be used for any levels of abstraction. Okay, so let us discuss about the switch level modeling. To discuss about the switch level modeling, what you guys need to have is, okay, what you guys need to know is the transistors diagram, that is nothing but CMOS diagram of AND gate. You need to know it. Since we are going to see the CMOS technology, right, so we need to know about it. If any other person is going to choose some other technologies like NMOS, only PMOS, pseudo NMOS, like this, then you need to know AND gate in those technologies. Most commonly in our academics we are going to discuss about the CMOS technology. So I am going to discuss in the CMOS technology itself. In switch level you are going to have so many levels of codings. Switch level with the help of the CMOS diagram, switch level with the help of the pseudo NMOS, switch level with the help of the only NMOS, only PMOS, like this. Okay, but in general mostly all the people use CMOS, so that I am going to discuss about the CMOS itself. So that for the gate level model you need to know the gate structure, how those gates are connected. You need to know that details. And for the data flow model you need to know the boolean expression. For behavioral modeling you need to know the truth table of the design. For switch level model likewise we need to know the how our design is got connected in a connected, or how our design is arranged in the transistor level, you need to know that particular diagram. Okay, let us discuss the theoretical part and come back to coding. Okay, so in my previous class I have told you, right? So we are taking the CMOS technology. We are going to take the CMOS technology. Okay, so CMOS technology is nothing but it is going to have two networks. One is the pull up network, the pull up, it is pull, okay, PULL, pull up network, and the other is pull down network, pull down network, PULL, pull down network. So the pull up network consists of PMOSs. Okay, in pull up network you are going to have PMOS transistors. PMOS transistors you are going to have in pull up network, and in an pull down network you are going to have NMOS transistors. Okay, now for the pull up network you are going to give the high voltage, high biasing voltage, that is VDD. It is called as VDD. For pull up network you are going to give the low biasing voltage, that is VSS. And to both pull up and pull down network you are going to apply the input. Okay, and from the common point of pull up and pull down network you are going to take the output. This is the common point, right? If you are going to join like this, this is the common point. From this point you are going to take the output. Okay, next, so these things I already discussed in the NOT gate video, and also I have discussed in the NAND gate video. If you haven't watched the video, I recommend you guys to watch those videos. Okay, so how will be our PMOS looks like? Let us see. It is the PMOS, right? See, PMOS will be seen like this. It is going to have total 3 terminals. One is gate, another is source, and then drain. We are going to always apply input at the gate terminal. Okay, let us see the NMOS as well. This is the NMOS. If you are going to see the image or the diagram, this is the NMOS, source, drain, and then gate. We are going to apply our input at the gate terminal of both PMOS and NMOS. Okay, and we are going to apply the biasing, that is high voltage and the low voltages we are going to apply to the source terminal. Okay, and we are going to have a common connection to both PMOS and NMOS with the help of the drain terminal. Okay, and you need to remember a point. PMOS will be on. When will be the PMOS will be on? Whenever, if your input at gate terminal is 0. Okay, if the input is 0, then PMOS will be on. Okay, if your input is 1 at NMOS, then PMOS will be on. Okay, next, if your input is 1 at the gate terminal of PMOS, then your PMOS will be off. Okay, you need to remember these things. Okay, if your input at gate terminal is 0, then NMOS will be off. Okay, you need to remember these points. Next, now in the NAND gate video, if you have watched the video, I have discussed about the some points. Why CMOS is called as complementary metal oxide semiconductor. Why complementary means at the output you are going to get the complement operation. Means in CMOS the basic gate is the inverter or the NOT gate. It is not the buffer. Okay, to make buffer, what you guys need to do is in CMOS you need to connect two NOT gates in a cascading manner. Okay, in CMOS the basic gate is NOT gate or the inverter. If you want the buffer, then what you guys need to do is you need to connect two NOT gates in a cascaded manner, okay, or in a series manner. So now the point is why the CMOS is called as complementary means at the output we are going to get the complemented outputs. Okay, this is clear. So in the previous case, if you remember, I have told you a point that if your boolean expression is going to have whole bar, then it is easy to make it is easy to get the CMOS diagram, right? So now we are going to work with the AND gate, right? So first of all, write the AND gate boolean expression A dot B, right? A dot is nothing but the AND operation, right? Now if you are going to see this particular expression, it is not going to have whole complement, right? So it means it is difficult to write the code. It is not, I'm not going to tell you that we can't able to write the code. It is difficult. Okay, so the first step, if your boolean expression is not going to have the whole complement, the first step what you need to do is you need to give two whole complements. Why we are going to give two whole complements means we know that, right, from the digital logic design we know that a bar whole bar will be equal to a, right? For the first case, if a is 0, then 0 bar will be 1. Later 1 bar will be 0, right? We got the a, right? If a is 0, then 0 bar will be 1. 0 bar over bar. If a is 0, 0 bar over bar will be 1. 0 bar will be 1. Then 1 bar will be 0, right? Again we got the a, right? Okay. So this is the property in the digital logic design. Okay. So okay, it means we haven't changed our expression, right? We are going to get the same logic. So if you are going to observe clearly, we are going to have two logic gates in this particular expression. See, one is NAND gate. If we are going to see it, this is the NAND gate, right? And a bar, we are going to have it. This is the NOT gate, right? This is the NOT gate, and AB bar will be the NAND gate. Means how we need to get this particular AND gate means by combination of NAND and NOT gate. Means you are going to take the NAND gate, you are going to connect the NAND gate output to NOT gate. We are going to apply the inputs to the inputs of NAND gate, and we are going to get the output at the output of NOT gate. We are going to get the AND operation. This is how we are going to design. Now we are going to replace this NAND gate with CMOS NAND gate. We are going to replace this particular NOT gate with CMOS NOT gate. Let us replace it. So I am going to do you on, I think I will explain it. Okay, no problem. So the first thing, how to design the NAND gate? Simple. You first need to see how many variables you are going to have. Here we are going to have two number of variables, right? A and then B. A and then B. Here we are going to have two variables, so that in pull-up network you are going you should have two PMOSs, and in pull-down network you should have two CMOSs for the NAND gate, right? It means we are going to take two PMOS in the pull-up network and two NMOS in the pull-down network. Why? Because we are going to have total two variables. Okay, we have known that we require two PMOS and two NMOS in pull-up and pull-down network respectively. Now, how those PMOS and NMOS needed to be connected with each other? For that, what you guys need to do is you need to see the operation in between the variables. If it is the product or the AND operation, then you should connect the PMOSs. You observe my wordings. I can't able to write over here. Why? Because the video length will be very high. If you want the writing part also, I recommend you guys to watch the NOT gate. I will just tell you in a oral way. Okay, see, you need to see the operation in between the variables. If the operation in between the variables is product or the AND operation, then the PMOS transistors in the pull-up network needed to be connected in the parallel. Means product operation, PMOSs needed to be connected in parallel. That's it. In NMOS, what you need to do is you need to connect them as series. Okay, so let us take the two PMOSs and connect them in parallel. Connecting two PMOSs in parallel is nothing but, let me show you. You are going to take the two PMOSs like this. This is one PMOS. Assume it as P1. Okay, and let me take another PMOS like this. This is PMOS 2. Assume it as P2. Now connecting two PMOSs in parallel is nothing but simply you are going to join the two source terminals of two PMOSs. Those are S1 and S1, S1 and S2. This is S1, this is S2. Okay, and joining the drain terminals of two PMOSs, that is D1 and D2. We are going to join them. Now what about the gate terminals? If you remember, I told you, right, we are going to apply the inputs at gate terminals. Okay, for one gate terminal you are going to apply one input, which is A in our case. For another gate terminal we are going to apply the second input, that is B. Okay, now where we need to apply the biasing voltage, at the source or drain? I told you, right, at the source common point where both the sources are joined, you need to give the biasing, high voltage biasing, that is VDD. Okay, and what you guys need to do, the drain you should extend like this. Okay, now our pull-up network is completed for the NAND gate. So pull-up network, what we guys need to do is we need to connect NMOS transistors in series. Connecting in series is nothing but, see, you take the both are two NMOS transistors. This is one NMOS and this is another NMOS. Let the NMOSs be, this is N1 and this is N2. Okay, so connecting two NMOSs in series is nothing but, let it be the source 2 and it be the drain 2 and it be the source 1, let it be drain 1. Is nothing but connecting in series, nothing but connecting drain terminal of one NMOS transistor with source terminal of another NMOS transistor. If you are going to connect like this, then we can able to say that both the NMOS transistors are connected in series. Now what about this particular source 2? We are going to connect this particular source 2 with low biasing voltage, that is VSS. Okay, I hope you understood. Now what about the gate 1 and gate 2? of NMOS N1 and then PMOS NMOS N1 and then NMOS N2. For these terminals also we are going to apply our two inputs. For one terminal we are going to apply our first input. For other terminal we are going to apply our second input. Now what about this particular drain? Simply we are going to join both the drains of NMOS both the drains of pull up network and pull down network. From this common point we are going to take the output, right? This is the output of NAND gate, right? Now what we are going to do is we are going to take this output and we are going to connect it to the inverter. How the inverter is made? Inverter expression, if you are going to see it A bar, right? For example, if I am going to assume this particular output of NAND as some X, then we need the X bar, right? Inverter operation is nothing but we need the X bar operation, right? So if you are going to see how many variables we are going to have, only one variable, right? So that one PMOS needed to be in pull up network and another PMOS will be needed to be in pull out network. Means total two transistors we need. One is PMOS and one is NMOS. One is in pull up network and one is in pull down network. So let us take them. This is PMOS and this is NMOS. Give the name these to this particular transistors as well. So I am going to give this PMOS as P3, okay, and this NMOS as N3, and you just name the source and drains. This is source 3 and then this is drain 3 and this is same drain 3, source 3, okay. It will be the gate 3 and then it will be the gate 3. Now what we need to do to the source 3 terminal, we need to connect it to the high biasing voltage. Again we are going to connect it with the VDD, high biasing voltage only. What we are going to do with the source 3 of N3, we are going to connect it with the low biasing voltage, that is VSS, okay, VSS. Now we are going to join both the drains of P3 and N3 and we are going to apply the input to both the gate terminals of P3 and N3, and we are going to take the output from the common point of both the PMOS and NMOS transistors. It will be our output Y, which gives our required operation, that is AND gate operation. So this is how we are going to make our AND gate, which requires a total of 6 transistors. In that 3 are PMOS transistors and 3 are NMOS transistors. I hope you understood how I bought this particular AND gate CMOS diagram. This is so simple, okay. If you are going to practice 2 to 3 times, then you can able to understand it. So let me use this particular diagram and write the code in switch level model. So see, now in our gate level model we are going to have the primitives for the gates, right? Similarly we are going to have primitives for the transistors in the switch level model. We are going to have PMOS in smaller case for the PMOS transistor, and we are going to have NMOS in the smaller case for the NMOS transistor, okay. So let us write the pull up network, this particular pull up network first. Okay, before that, what we are going to do is, let us see whether we are going to have all the inputs or not. We are going to have A and then B and then Y. We are not having the supplies, right? Supplies, right? VDD and then VSS. So do you need to mention them in the port list? No, you shouldn't mention them in the port list. And make sure you remove this particular edge, okay, at the output. Only whenever you are going to use the behavioral model, then you need to use the output as reg. Okay, now you shouldn't give the supplies in the port list. Okay, you need to give in between the semicolon and the end module in the work or logic area. So how we are going to give it? For those, for that you are going to have keywords like supply 1. Supply 1 is nothing but the high voltage. VDD means VDD is the high power supply. Okay, high voltage. Okay, supply 0 means 0 means low, right? VSS is the low voltage. Okay, like this we are going to give the biasing, we are going to declare the biasing voltages. Now let us write the code for this particular pull up network. Let me change the ink to some, let us take yellow. Yeah, no, let us take some black. Yeah, so let us write the code for this particular region. Okay, so we have the primitive, right? PMOS, and you need to give the instance name. Instance name is nothing but, we are going to have several number of PMOSs in our code, right? We need to differentiate them, so that we need to give them a name. I am going to give the name as P1 and the open parenthesis and then close. What you need to give in the inside the parenthesis is nothing but the parameters. How many parameters you need to give? Okay, how many parameters that you need to give? How many parameters that you need to give is depends upon the how many number of inputs that particular transistors, how many number of terminals that particular transistor is going to have. For this particular transistor, you are going to have 3 terminals. One is gate. For any transistor, PMOS or NMOS, you are going to have 3 terminals: gate, source and then drain, right? So that you need to give 3 parameters inside the parameters. Okay, we have known that. Okay, now in which order you need to give it? Is there any order? Like you should specify the gate terminal first, later source, and then later drain, like that. Do we have any order? Yes, we have a order. How to give that? First you need to specify the drain, means you need to specify what is connected to the drain terminal. Later you need to specify what is connected to the source terminal, and then later last you need to specify what is connected to the gate terminal. Okay, so for the drain D1, what is connected? For the drain D1, D2 is connected. Okay, and we have taken this common point and we have given it as name as X, right? Is there X in our declarations? Is there X in our declarations? We have A, we have B, we have Y, we have VDD, we have VSS. Is there X? No, right? So that we need to declare it. How we are going to declare it? As a wire or a reg? Is X is a wire or reg? It's a wire, right? We need X needed to flow to this particular inverter diagram, right? Inverter circuit. It is X is continuously wanted to be flowed to send the value to the inverter circuit, right? So X will be the wire. It is not reg. Why? Because if you are going to take it as reg, then it is going to just simply store it. But you need X value to be wire. Why? Because it is connected to the inverter circuit. Okay, I hope you understand it. It is needed to continuously driven to the inverter circuit, so that wire X. Okay, and in the parenthesis you specify the X. Why we are going to specify X? Because for the drain terminal P1, X is got connected. Next, for the source terminal of P1, what is got connected? For the source terminal of P1, what is got connected? Source terminal of P2, and both of them are connected to the VDD, so that you need to mention VDD. Okay. Similarly, for the gate terminal of P1, what is got connected? One of the input, that is A. Like this you need to give it. Now you just copy it. Now we have completed our P1. This part is completed. Now let us use another PMOS instance or the PMOS primitive, and then modify it to get the P2. So you need to change the name to P2, and what is got connected to the drain terminal of P2? Drain terminal of P2 is connected with the D1, so that both of them were connected with the wire whose name is X, which we have already declared, right? So that we are going to leave this value of X as it is. Next, source 2, source terminal of P2, that is source 2, where it is got connected? It is got connected with the VDD, so that we have given VDD. Later, gate 2, that is gate terminal of P2, to which variable or the signal it is got connected? To the B, right? So that you need to replace this A with B. Now we have completed our pull-up network. Okay, let us see the pull-down network as well. For pull-down network, what you are going to have? You are going to have the NMOSs, right? So that we are going to use the NMOS instance or the primitive name, and we are going to give the N1. First, initially we are going to write the instance of NMOS N1. Okay, inside this parenthesis, how many values or the parameters you need to give it based on the number of terminals that a transistor is going to have. This particular transistor is going to have 3 terminals again. Those are drain, source, and then gate. How should be the order? How should be the order? Like first we need to specify the gate, later drain, and then source, or any specific order? Yes, the same order we are going to have, which is therefore PMOS. First you need to specify the drain, later source, and then gate. Means first you need to specify for drain terminal what it is got connected with, and for the source terminal what it is got connected with. Later you need to specify the gate terminal to which signal it is got connected. So let us see the drain terminal, that is D1 of N1. It is got connected with the D2 of P2 and D1 of P2, and together they got connected with the X, right? So that you need to give X. Next, now the source terminal of N1, to which value it is got connected? The source terminal of S1 is got connected with the D2. For this particular wire, did we give any name? No, right? We haven't given any name. So let us give this particular wire as Z, name as Z. Did Z contain in our program? Did we declare our Z? No, right? So that we need to declare it. How we need to declare it? As a wire, or a edge as a wire, right? Because it is needed to continuously driven, right? So that we are going to declare the Z signal as wire. I hope you understand it. Z signal as wire. We have declared it, and I am going to give Z over here. Okay, these signals are internal signals, so that we are not going to specify them in the port list. Okay, these are the internal signals which we can't able to see outside. After the chip manufacturing, we can't able to see these particular wires. Okay, we can able to see only inputs and outputs. We are not going to see the internal wires. Okay, after the chip manufacturing. So at the gate terminal, what it is got connected? Gate terminal of N1, we have connected with A, right? So that you need to give A. Just copy it and take a few seconds and tell me. You just take a few seconds and pause the video and write the values of N2. Okay, so first, for the drain terminal, what we have connected? Drain terminal of N2, what it is got connected with? It is got connected with the Z, right? So replace X with Z. Later, for the source terminal of N2, what we have connected? We have connected the low bias voltage, that is VSS. So you just replace Z with VSS. Later, the gate terminal of N2, to which it is got connected? It is got connected with the another input B. So that replace A with B. Now we have completed our NAND gate. This part is completed. Now what the other part is left is this part. Let us do it. Okay, now for that we need to take two instances. One is PMOS instance and another is NMOS instance. Let me take it. Now you change the name of this particular instance as P3. Okay, now for the drain terminal of P3, what we have connected? We have connected it with the drain terminal of N3, and both of them connected with the output Y. See, do we have the Y, right? We have already given it in the port list, so that you need to replace X with Y. Now for the source terminal of P3, what it is got connected with? It is got connected with the VDD. Okay, so just leave as it is. And next, the gate terminal of P3, to which value it is got connected? It is got connected with the X, right? Which is the internal wire, which gives the NAND operation, right? So replace B with X. Okay, similarly you do it for the NMOS. Okay, for NMOS, what happens? For the drain terminal of N1, sorry, you need to change the instance name, right? N3. Why? Because you shouldn't use same instance name. Okay, for two NMOSs, or it may be for the two PMOSs. So for the drain terminal, we have connected the output Y, right? So that you need to replace it as Y. See, next, the source terminal. For the source terminal, we have connected the VSS, so that you need to give it as VSS. And for the gate terminal, we have connected the internal wire, that is X, which gives the NAND operation, right? Now we have completed our code. It's so simple, right? If you are going to have the CMOS logic diagram, then it is so simple to write the code. We have completed our code. You can see total 6 transistors are there. 3 are PMOS transistors and 3 are NMOS transistors. 3 PMOS transistors will be in the pull-up network and 3 NMOS transistors will be in the pull-up network. Now you need to run this code and you need to observe the output whether you are going to get the correct output or not. So for that you need to select the tools, go to the tool, select the first tool and then save it and then run the code. Now you are going to see the output, right? For both input test cases 1, we are going to get the output as 1. Output test case as 1. For all other cases, we are going to get output as 0. Which is the functionality of our AND gate. Means we can able to say that the design code is perfectly working as a, this particular design code is perfectly working as a AND gate. To see the waveforms, what you guys need to do is, you need to click on the open EPWave after run. You need to save the code again and rerun it. If you are going to rerun it, then what happens is a waveform window will be popped up to you automatically like this. So here there is a I, right? I is nothing but the iterator which I have used in the test bench. If you want the detailed explanation about the test bench, then you must watch the AND gate using the gate level model. Then in that video I have discussed it. Okay, you just select it and delete it and observe the output. For all the inputs test cases as 0, we are going to get output test case as 0, and for test cases, input test cases as 0 1, we are going to get output test cases 0. For 1 0, we are going to get 0. For 1 1, we are going to get 1. Means only when input test cases, all the input test cases are 1, we are going to get output test cases 1. For all other cases, we are going to get output test cases 0. This is how we are going to see the output. If you need the timing details as well, I recommend you guys to watch the AND gate video using the gate level model. In that I have discussed about this timing. Okay, so that's it for the video. I recommend you guys to have an hands-on experience. And not only CMOS, if you are really interested about something like if you are really interested about writing code, then you choose any other logic like only PMOS, pseudo NMOS, like this kind of logics, and write the code in this switch level model by your own. Okay, thank you, have a nice day.